All right, hello class. My name is Isaac Joseph, and today I'm going to be presenting my project number 2. We're going to be talking about covariance and correlation in statistics. So let's start off right away and check out our question over here. We're going to jump right into this question over here, and this is kind of what we're given. We're given this, the diagram here. We're given these two equations. We're given this equation for the shear force Q and the moment M. We're also given that S1 and S2, these random forces, are going to be independent. We're given the mean values of S1 and S2, and we are also given the standard deviation values. So we're going to hop into the first part of this question. We are asked to find the mean and variance of Q, the shear force, and M, the moment. So we can set this up. Start off, we're going to be looking for the mean of the Q, the shear force. And we know that the mean of a random variable is going to be the expected value of that random variable. So in this case, we can express it as mean of Q is equal to the expected value of Q, or E of Q, which is equal to the expected value of S1 plus S2, because that is the equation given for Q. Now, back to these equations over here. These equations exist for instances when we have independent random variables. So in this case, we have for our expected values that a times x plus b times y, where x and y are independent, is going to be equal to a times the expected value of x plus b times the expected value of y. And we also have it for their variance as well, where the variance of ax plus by is going to be equal to a squared times the variance of x plus b squared times the variance of y. So using this relationship here, we're going to find that the mean of S1 plus S2 is the same as the mean of S1 plus the mean of S2, or the expected values. So the mean of Q is just going to be mu1 plus mu2, because those are our expected values of S1 and S2 that we're given. Moving on to the mean of M, we have that the mean of M is equal to the expected value of M again, which is going to be equal to this equation that we're given for M in terms of S1 and S2. So we have that this is the expected value of A times S1 plus 2A times S2. And again, going back to this equation here, we do have these random variables being scaled by our certain parameters here. So we can use this relationship again to say that A times the mean of S1 plus 2A times the mean of S2 is going to be equal to the mean of the value M here, which is going to be A times mu1 plus 2A times mu2, the expected value of S2. So now moving on to the variance, we have our means of Q and M. We want our variances as well. So we have our variance of Q is going to be equal to the variance of S1 plus S2. Again, we're just going to express Q in our equation that we're given here. And using this relationship here, we can see that the variance of x plus y is going to be the variance of x plus y, since there is no scaling on either of these terms. So the variance of Q is just going to be the standard deviation of S1 and S2, and both of them are going to be squared, because as you can see, the variance of S1 and the variance of S2, the square root of those is equal to sigma 1 and 2, so the variance is going to be equal to sigma 1 squared and sigma 2 squared, and that is what is represented over here. So moving on to the variance of M, we're going to do the exact same thing here. We're going to have the variance of M equal to the equation of M, and here we can see that these S1 and S2 random variables are actually being scaled by a factor of A and 2A here. So when we set this up in this equation, we can't just break it up individually here. We have to go by this relationship here, which says that the scaling factors are going to be squared. So we have A squared times the variance of S1 here, and we have 2A squared, which is going to be 4A squared. 2 squared A squared, which is 4A squared. And that is going to give us our variance of M as A squared, sigma 1 squared, plus 4A squared, sigma 2 squared. So next in this question, we're asked to find the correlation coefficient. Correlation coefficient that we're being asked for over here. And we have this relationship where our correlation coefficient rho is going to be equal to the covariance of the two random variables divided by the standard deviation of both of those variables, or the product of their standard deviations. So you may be asking yourself, what is a correlation coefficient? Well, a correlation coefficient is a coefficient which, as the name implies, describes a correlation between two data variables in a data set. So this correlation coefficient, which we are going to be calling rho, of let's say x and y, just for example, this correlation coefficient can span between -1 and +1. So if we were going to look at our correlation coefficient on a graph such as this, where we have 0, 1, and -1, how can we describe the correlation or how well related two variables are in a set of data? When we have our graph, like so, of a set of data points, we can say that it will have a high. In this region, we're going to have a strong correlation, a strong positive correlation, and in this region over here, we're going to have a strong negative correlation because they are going to be closer to these 1 values. So a strong positive correlation might mean that the data points that we have look something like this, where it has a positive slope and they are strongly correlated. These data points are close to each other with relation to each other. And anywhere where we're going to have a lower or like closer to 0 value over here, or even a negative closer to 0 value over here, that is going to be a positive or negative, like weak or lesser correlation. So the covariance between two random variables is going to be the expected value of the product of these two random variables minus the product of their means. So we're going to start off, in order to solve this correlation coefficient, by finding this top part here, the covariance, which is going to be equal to this equation right here. This is a super important equation which describes the covariance of these two variables. So we have that the covariance of Q and M is the expected value of Q times M minus the mean of Q times the mean of M. Our expected value of Q is going to be mu1 plus mu2. Expected value of M is a mu1 plus 2a mu2. So we can see that we plug those into our expected value right here, and we're going to be taking the product of those minus the product of their means, which these are the means that we also just solved for above. So our first step is to put our values into this equation, and then we can go ahead and start multiplying through and expanding these brackets. So we're going to get this relationship here when we expand these two brackets minus this relationship here when we expand these two brackets right here. So that's what we're doing in this next step, is just multiplying through, and our goal here is that we're going to be trying to factor as much as we can in order to simplify and solve for the covariance. So here what we're actually going to do is we are going to use our relationship once again that we were using above here, where we say that the expected value of ax plus by is a times the expected value of x plus b times the expected value of y. So we can say that the expected value of all of the sum of these terms, this term, and this term, is going to be equal to, like, for example, this term, a times the expected value of s squared 1. But next, we need to talk about our second moment, because in this equation over here, where we're looking for our expected values, we need to know the expected value of the s1 squared. And we also need it for s2 squared over here. So this is going to be called our second moment. We talked about this in class, where our second moment, the equation for the expected value is going to be the variance of x plus the expected value all squared. So the second moment here is going to be equal to the variance times the expected value of the first moment all squared. So we found our second moments. We're going to plug these into our equation here and here, and we already know these expected values here. So we have that our initial bracket here expands out to just being this relationship here, where we have plugged in our second moment at this point and this point, and we also still have our remaining relationship here for the product of their means, and we can now begin to simplify this term. And if we multiply this whole bracket by -1, we are going to be subtracting it from the expected value products. We are going to be able to simplify quite a few terms here. So we started off by factoring out an a, and then we proceed to simplify this just to make it a little bit easier to look at. And we find that the covariance of Q and M is going to be equal to this relationship right here. So moving on, we have our covariance. That is going to be the hard part of this problem, find the coefficient, the correlation coefficient. So now we can plug this value in of our covariance into our equation for rho, and we can solve our correlation coefficient. It is asking us for the variance of Q and M, which we had, the standard deviation product of Q and M, which we had solved for their variances. So what we're going to do is we're going to take their variances and we're going to multiply them by each other, but we are going to take the square root of the entire bracket, because if you recall, the standard deviation is equal to the square root of the variance. So at this point, the product of their variances is the product of their standard deviations is going to be equal to the product of their variances, all square rooted. So our correlation coefficient in the end is going to give us this relationship right here. So the last part of this problem is asking us to find the correlation coefficient when sigma 1 is equal to sigma 2. So in this relationship, we've already solved our equation for the correlation coefficient rho. So all we have to do is set sigma 1 equal to sigma 2. So wherever we see a sigma 2, we're just going to plug in sigma 1 in this case. Or we can do it the other way around. It really doesn't matter. It simplifies down for us further, and we can factor out the sigma 1 squareds, and we get that the correlation coefficient is going to be equal to 3 over root 10, which is 0.949 approximately. So looking at this value of rho that we have, we can say that since it is very close to 1, positive 1, we can say that our data points here, Q and M, have a strong positive correlation with one another. And that is my project for you guys. Thank you for listening.